Today, I just want to really scratch the surface and maybe give a historical perspective of what we've done at the University of Texas at El Paso and what we call 3D printed multifunctionality. Really, we've been trying to do 3D printed electronics for about 20 years in different formats, different materials. And I'll just sort of give an overview of what we've done, sort of what, really took off in terms of the projects that sort of captured the imaginations of funding agencies in the United States. But you see some examples below of different polymers with conductive inks and with chips, with the idea that we wanted to basically compete head to head with printed circuit boards, but we wanted to, add the third dimension. And so a montage that kind of captures the essence of this is here. Upper left, you have the ability to print complex geometries in ceramics, metals, and polymers. Most of the electronics work we've done was polymers, but we've recently had a project with University of Bremen and the Fraunhofer there, putting sensors in metal, and we're really interested in alumina. You can see in the upper left, there's an alumina piece, which has very good dielectric properties, but very good thermal conductivity, which is positive for high power electronics. Take those types of technologies on the upper left, combine them with the bottom left, traditional processes, laser ablation, robotic placement, this, deposition of inks, and you get this kind of wacky montage to the right. We've had some of these pieces flown in low Earth orbit. You see the red piece. The white circle is actually a zirconia with an aerosol jetted dipole antenna. The only piece that's not a part of really the UTEP heritage is the bottom left, which was done by Oak Ridge. And it's not electronic, but it has pneumatic controls within it. So we consider that multifunctional. And the bottom right, you have the dice, which is probably the dumbest thing we did, but everybody seems to understand it. It's a microcontroller, an accelerometer. It knows when it's rolling and moving and when it stops, and then it knows which way's up based on which direction gravity's pulling, and we blink the lights on the top. We try to commercialize that with casinos, and immediately they recognize that with 3D printing, you could spatially vary the density and, affect the odds of the dice and the outcome. So it never really went anywhere. And I'll tell you that in about 2009, we actually published this in 2013, so that's sad, but this was done in 2009 where we manually are inserting wires and components into an object as it's being printed during process interruptions. And we're making a motor. So there's a rotor and a stator, two separate mechanically independent pieces being printed simultaneously. And we're putting in magnets at this point. We'll then put in electromagnets that we've created. And so we have to re-register the piece when it comes in and out. This is the Keck Center at the University of Texas, El Paso. And one of my best students, Efrain Aguilar. And now here he's actually putting wires in, not conductive inks, because this motor had high power. And he's putting them into channels. We later had a patented process where we could submerge the wires into the thermoplastic, and I'll show some examples of that. Here's the final ball bearing, which separates mechanically the rotor and stator. And what you get then when you're done is an actual motor that runs at like 4,000 RPM. One of the things I wanted to do here, though, is I wanted to have a UAV or a robot walk out of the printer. But back in those days, and this is like 12, 13 years ago, the Stratasys printers were all, heated envelopes. So you couldn't put a battery into the object as it's being created because it was just too hot. And so here you see that working. And then here's Efrain. I think we're going to show his face. He's now at Texas Instruments. So about 2 years ago, just before the pandemic, I met a French researcher, Alexis Morel, who was working on 3D printed batteries. And so this was always my dream, to be able to print everything. Maybe place some components like magnets or microcontrollers, but in general, to put the whole system together, antennas, energy storage, programmability, actuation. And we've just gotten a NASA grant to do 3D printed batteries, sodium ion batteries using Martian regolith, trying to extract the chemistry from Mars so that they'll be able to print batteries there. We're hoping to get a Department of Energy grant for lithium ion batteries. But I think this is a very nascent area, and it's definitely a topic that will be interesting because of the complex interdigitated anode cathode architectures that you can create based on the freedom of additive manufacturing. So that motor video basically led to this America Makes funded project. And we have a conveyance robot. This is sort of overkill, but there's 2 Stratasys printers printing collaboratively. In this case, they're just using 2 different materials, but within the radius of that robot, we had many workstations. Really, the important one is about to show up right now. It's taking it out of the printer and going into another gantry where we have the traditional manufacturing processes, machining, robotic placement, deposition, and so forth. So we can interrupt the process, bring it to this system, this workstation, enhance it at several stages, and then continue. We had heard that NASA was going to have a X prize for, who could print a CubeSat in 24 hours. And so we were really hoping that that would come through. Here's a copper sheet, and we're machining it to do a ground plane, the complex geometry. We actually put in boards and so forth. We're about to put some electronics into a cavity, which we could then print upon subsequently. But you can see how you could do a component, but you could also do boards. Here, we're actually ultrasonically submerging a wire into a singly curved surface to make an antenna. And so we were really trying to get away from inks because we always struggled with inks having low conductivity, like we would see right here, and that using bulk wires had some advantages, and we were getting pretty good spatial resolution. So here you have 2 wires in a material that's not commercially available. It's being used in the New Balance shoe, and it's a design that I had done in Youngstown, Ohio. And there's 2 wires that are acting as a capacitive sensor to do deformation sensing. We were trying to get money from the National Football League in the United States, an organization that's trying to lower the number of concussions. And I think that's all I've got. I know that this is already 6 minutes, but one thing I'd like to say really quickly is, coming back to inks, we're now looking at alumina and zirconia. It's not flexible, it's not stretchable, but it could certainly be conformal to human anatomy, replacing a bone or replacing a part of a satellite. And you could take these ceramic 3D printed complex geometries to much higher temperatures. And so we're really looking forward to the next generation of inks that can be cured at 850 C or above to get almost bulk conductivity. And with that said, I will now hand it off. Hey, thank you.